Assalamualaikum warahmatullahi wabarakatuh and selamat sejahtera. So our topic today which is kinetic theory of gases. So in this topic it will cover the elementary kinetic theory, application to the gas law, application to the gas law Maxwell-Boltzmann equations, probability density, transport phenomenon of gas, diffusion thermal conductivity and collision theory, and real gas. As we know, there are three common phases or states of matter, which is gases, liquids, and solid. Gas is a state of matter that has no fixed shape and no fixed volumes, which is it has lower density than the other states of matter such as liquid and solid, because there are great distance between these particles. Gases has three characteristic properties, which is they are easily to compress, they expand to fill their containers, and they occupy far more space than the liquid or solids from which they form. There is a great deal of empty space between the particle, which has a lot of the kinetic energy. The particle will move very fast and collide into one another, and causing them to diffuse or spread out until they are evenly distributed throughout the volume of the container. When the pressure increases, there is less space for the particle to spread out and they become compressed. So the particle will exert more force on the interior volume of the container. Figure shows the locations in the periodic tables of those elements that are commonly found in the gases, liquid and solid states. Except for hydrogens, the elements that occur naturally as gases are on the right side of the periodic tables. The noble gases in group 18 are monoatomic gases, whereas the other gases elements are diatomic molecules such as hydrogen, nitrogen, oxygen, fluorine, and chlorines. And the rest of the elements are all solids under the normal conditions. Table shows the some substance found as gases at 1 atm and 25 degrees Celsius. Gas substances include many binary hydrides such as hydrogen halides and simple covalent oxides of the non-metals of the gases such as carbon monoxides and carbon dioxide. And the ammonia and sulfur dioxide, which is widely used as a refrigerant, but it does not use in houses because of their poisonous nature. Atmospheric pressures, also known as barometric pressures, which is the force exerted against the surface by the weights of the air above the surface. All atoms and molecules of the gases in the Earth's atmosphere are held by the gravitational force of the planets. The atmosphere is much denser near the surface of the Earth than at high altitudes, which is at higher altitudes, the atmosphere pressure is lower and the air is less dense than at higher altitudes. And the density of air decreases very rapidly with the increasing distance from the Earth. Figure shows the simplest kind of barometer, which consists of a tall closed tube standing upside down in a bus of a mercury. Mercury is a dense liquid metal at room temperature, so that the liquid rises partly up the tubes, which is the concept is a bit like it does in a thermometer. Atmospheric pressure reduces with altitude for two reasons, both of which are related to the gravity. The gravitational attraction between the Earth and air molecule is greater for those molecules near to the Earth than those further away, where they have more weight dragging them close together and increasing the pressure, which is pressure is equal to force per unit area between them. And molecules further away from the Earth have a less weight because of gravitational attraction is less, but they are also standing on the molecule below them, which causing the compressions. Those lower down have to support more molecules above them and further compress or pressurize in the process. Gas particles are extremely small, so when the billions of gas particles hit the walls of the container, they can exert a force which is known as a pressure. Pressure is equal to force over area. Gas pressure is caused by the force exerted by a gas molecule colliding with the surface of the objects. Although the force of each collision is very small, any surface of appreciable area experiences a large number of collisions in a short time, which can result in a high pressure. The pressure of the gas can be increased by increasing the frequency of the collisions between the gas particles and the walls of the container. And the frequency of the collision can be increased by either one of two factors, which is increasing the temperature of the gas and increasing the number of moles of gas. As the temperature increases, the average kinetic energy increases, as does the velocity of the gas particles hitting the walls of the container. The force exerted by the particle per unit of area on the container is called as pressure. So that the temperature increases, the pressure must also increase. And the pressure inside the container is depends on the amount of gas inside the container, which is when increasing the concentration of gas particle inside the container will result in increase in the collision frequency between the gas particles and the walls of the container, and leading to an increase in the pressure of the gas inside the container. Pressure on Earth varies with the altitude of the surface, so air pressure on mountain is usually lower than air pressure at sea level. Pressure varies smoothly from the Earth's surface to the top of the mesosphere. As altitude increases, atmosphere pressure will decrease. The pressure at any levels in the atmosphere may be interpreted as the total weight of the air above a unit area at any elevations. Variations in weather also cause change in atmospheric pressure. Weather is ultimately caused by temperature difference due to the variations in solar energy input. This temperature difference causes pressure variation in the atmosphere. High and low pressure system evolve due to the interactions of temperature differentials in the atmosphere. Temperature difference between the atmosphere and water within the ocean and lakes. The influence of the upper level disturbance, as well as the amount of solar heating or radiational cooling an area receives. Low pressure systems are associated with the cloud and precipitations that minimize temperature change throughout the day, whereas the high pressure system normally associated with the dry weather and mostly clear skies with larger diurnal temperature change due to the greater radiation at night and greater sunshine during the day. A gas can be described in terms of four properties, which is pressure, volume, temperature, and amount of gas, or number of moles n. Pressure is the force exerted by a gas against the walls of the containers. Volume is the space occupied by the gas. Temperature determines the kinetic energy and the rate of motions of the gas particles, whereas n is the quantity of the gas present in the containers. Pressure can be expressed either in atm, millimeter of mercury, torr, pound per square inch, or kilopascals. And the SI unit for pressure is Pascal, which is Newton per meter square. The velocity is the speed of something in a given directions, and the velocity of an object is the rate of the change of its position with respect to a frame of reference, and is a function of times, which is equal to distance over times, whilst the acceleration is the rate of the change of the velocity of an object with respect to times. Accelerations are vector quantities in that they have a magnitude and directions. The orientations of an object's acceleration is given by the orientations of the net force acting on the objects, which is equal to change in velocity over times. While force is equal to strength or energy as an attribute of physical actions or movements, which is equal to mass times accelerations. A barometer is a scientific instrument used to measure atmospheric pressure, or also called as barometric pressure. A Jerusalem barometer, or sometimes called as a mercury barometer, is inverted upside down a glass tube standing in the bath of mercury. Air pressure pushes down the surface of the mercury and making some rise up the tubes. The greater the air pressure, the higher the mercury rise. Actually, you can easily use a DIY barometer, which is you just take a glass bottle and turn it upside down and put the neck into a bowl of motor oils. When the atmospheric pressure increases, the air levels in the bottle will rise, and when the pressure decreases, the oil level in the bottle will fall. At the sea level, the pressure of exactly 1 atmosphere caused the mercury columns in the barometer to rise exactly 760 mm mercury high, which is 1 atm is equal to 760 mm mercury, and also equal to 760 torr, or 76 centimeter mercury.
Let's see the instrument used to measure atmospheric pressure. We have this simple barometer, 14 barometer, and aneroid barometer. Simple barometer, 14 barometer, aneroid barometer. Okay, as I told you just now, our focus is on this simple mercury barometer. Now let's start with a simple barometer. So atmospheric pressure can be measured by a simple barometer, and this is a simple barometer. Now, how to build this simple barometer? This is mercury. This is mercury. We use mercury is because mercury has very, very high density. If the density is not high, then this tube must be this tube must be very, very high. If you use mercury, then this tube can be just around 1 meter high. So what we do is we have a container filled with mercury. We have a long tube. You fill it with mercury and then close it. Fill it full with mercury. Okay, full with mercury and then close it. And after you close it, place this open end into the container that contains the mercury and open the hole. When you open the hole, initially the mercury is full. Okay, this is full with mercury. But after you open the hole, the mercury will go down. Okay, it will go down up to certain level. Okay, it will stop. It stops because there is atmospheric pressure press on the surface. The atmospheric pressure press on the surface. So when the atmospheric pressure press on this mercury, okay, so these mercury levels, okay, it will go up to a certain level where the pressures of this column of mercury same as the pressures of the atmosphere, and then it will stop. Okay, it will stop here around 76 cm. Okay, 76 cm means that the pressures of this mercury column is the same as the mercuries of the atmosphere. So that is how we built this simple barometer. Okay, simple barometer. So now you know why this level is higher. Okay, this level is higher is because there is atmospheric gas pressed on the surface of the mercury and press and move the mercury into the glass tube, and force it go to a certain level. Okay, until the pressure inside here is same as the pressure outside, then it will stay at this level. So that is a simple barometer. So a thick glass tube at least 1 meter long is filled with mercury completely, and then the open end of the tube is covered with a finger and inserted it in a trough of mercury. The height of the mercury is proportional to the atmospheric pressure. So the height, okay. So we can measure the atmospheric pressure by measuring the height. Now for a simple mercury barometer in exam, they may give you two types of questions, so you must be very careful. The first one is inside the tube, okay, this is labeled vacuum. This is vacuum. Okay. Another one is there are some gas trapped in the tube. Vacuum and some gas trapped in the tube. Okay. So for those simple, suppose it's vacuum, suppose it's vacuum, but sometimes they may give you questions where gas trapped in this gas tube. Okay. So for a barometer where there's no gas inside this tube, it's vacuum. The pressure at A is equal to X cm mercury. Okay, as I told you just now, right? For mm mercury or cm mercury, the pressure is equivalent to the length of the mercury column. Okay, if this is 30 cm, then the pressure at A is 30 cm Hg. Then how about the atmospheric pressure? Okay, now for atmospheric pressure, you need to know something. Okay, first you need to know that on the surface here, the pressure here is equal to the atmospheric pressure. The pressure on the surface, the pressure on the surface of a liquid is equal to the atmospheric pressure. Okay. Last week we learned that for liquid pressure at same level, okay, this point here, they are at the same level, right? So let's say this is the P, okay. P, okay. Let's say this is a P1. Okay, so P1 and this surface are at the same level, and therefore the pressure must be the same. So P1 must be equal to the atmospheric pressure. Why? Because they are in the same liquid and at the same level. Okay, same liquid at the same level, the pressure must be the same. Okay, the pressure must be the same. Then what is the pressure at this point? Okay, the pressure at this point is equal to H cm mercury, right? Okay, because the pressure in mercury is equal to is equivalent to equal to the length of the mercury. Yeah? So the pressure at P1 is equals to H cm mercury. So the atmospheric pressure is equal to, since the atmospheric pressure equal to P1, so atmospheric pressure equals to H cm mercury. Okay, H cm mercury. Yeah. So for this case, the atmospheric pressure is equals to 76 cm mercury, or 760 mm mercury. So that is how we measure mercury. Just tell the length of the mercury. Okay, 76 cm. Okay, from the surface, from the lower surface to the upper surface. That is the atmospheric pressure. That's how easy we use a simple barometer to measure atmospheric pressure. Okay, just tell the length. That is the atmospheric pressure. When you use the simple barometers, okay, then the unit of the pressure that you get is in cm mercury, right? Cm or mm mercury. Okay, let's say you have a simple barometer, and then you measure the pressure. Again, you'll find that the pressure is 75 cm. Okay, 75 cm. So therefore, the atmospheric pressure is equal to 75 cm mercury, right? Cm mercury. But sometimes, especially in objective questions, they may want you to convert this to Pascal. They may want you to convert this cm mercury to Pascal. So how to convert cm mercury to Pascal? So what can we do is we use this formula. Okay, yeah, we use this formula because this formula is for you to find pressure in Pascal. Okay, H rho g. This is the formula for liquid pressure, right? Yeah, pressure that caused by liquid. Okay, so for this case, let's say the length of the mercury, the length of the mercury is 75. So the depth is 75 cm, right? Okay, 75 cm. If you want to write in Pascal, you must convert the cm to meter. You must write, if you want to write your unit in Pascal. So 75 cm is equals to 0.75 meter. And then you multiply by the densities of mercury. Densities of mercury, usually it will give you in exam 13,600. Okay, 600. And G is the gravitational field strength, which is equal to 10. And then you get your answer in Pascal. That is how we convert unit of cm mercury to Pascal. We use P equal to H rho g. P is the length of the mercury, but must be in meter. Rho is the density, usually is given in the questions, and G is the gravitational field strength. Okay, then you can find your answer in Pascal. Okay, so that is how we convert cm mercury or mm mercury to Pascal. Find the pressure at point A, B, C, D. We have 2D here. A, B, C, D, E, and F. Okay. Let's start. Okay, so first they want you to give in cm mercury. Yeah? So what's the pressure at point A? This is vacuum. Okay, this is vacuum. This is vacuum. Okay, the pressure at point A, because A exposed to the vacuum, and the pressure of vacuum is 0, so the pressure at point A is equal to 0. 0. And in Pascal also 0. Okay. How about the pressure at B? Okay, it's 17 cm from the surface, right? B, yeah? So it's a 17 cm mercury. Then how about Pascal? How about the pressure in Pascal? Okay, now you can do this by using the H rho G. The H is 0.17. The rho is the density. Okay, I should give you the density. Yeah, okay. Densities of mercury is 13,600 kg per meter cube. So multiply by the density 13,600 and then multiply by G 10. Then you get your answer. Okay. Pressure of B in Pascal. How many Pascal? 23120. Okay. 23120 Pascal. Pascal or Newton per meter square. Newton per meter square. Then how about C? What's the pressure at C? PC. Okay, C is 17 cm plus 59, right? Okay, the length of the column. Okay, 17 plus 59. So it's a 76. 76 cm mercury. How about D? What's the pressure at D? Tell me your answer in a cm mercury. D. What's the pressure at D? Now, let's say you have another point at this level. Okay, same level, same pressure, right? Okay, so 76 plus another 8. 76 plus another 8, 84. So A to C, 76. C to this point plus another 8 cm, 84 cm. Okay, so at these levels, the pressure is 84. 84 cm mercury. Then how about pressure at E? Now E and C is at the same level. E and C, same level. Same level, same pressure. PC 76, PE must also be 76. Okay, so that's why we say the length of the mercury is equal to the atmospheric pressure, because the pressure here and the pressure here must be the same. How about F? How about F? What's the pressure at F? The answer is not 17. Okay, it's not 17. Why? Because same level for same liquid, then the pressure is the same. But this is not the same liquid. This is in the air. This is inside the liquid. So even though they are same level, their pressure should not be the same. So same level, same pressure only apply to same liquid. Same liquid. Okay, this point and this point, yes, on the liquids. Okay, this one and this point, okay, but this point and this point cannot. It cannot be 17. Okay, and this point and this point, okay, the distance is very close to each other's, right? And then I told you that for gas pressure, okay, the pressure act equally at each directions. Okay, so if the pressure here is 76 cm mercury, the pressure at F must also be 76 cm mercury. Okay, because this point and this point is acted by the same atmospheric gas. The same atmospheric gas. Here also 76, here 76, here 76, here 76. Okay, every point outside the barometer is 76 mercury. That is the atmospheric pressure. 76, here 76, a little bit higher 76, okay? Because this is the atmospheric pressure, the pressure caused by the atmospheric gas. The gas pressure, the gas press on this point, okay? The pressure is the same. So it's a 76 cm mercury. This is vacuum, 16 cm, 90 cm. Figure 1 shows a simple mercury barometer. What's the values of the atmospheric pressure shown by the barometer? Okay, tell your answer in cm mercury. So what's the atmospheric pressure? Tell your answer in cm mercury. Yeah? How many cm mercury? 74. Okay, yes, that's correct. Okay, how to get 74? Okay, we take 90 minus 16, right? Okay, this length is 90 minus 16. Okay, so it's equal to 74. Huh? So it's 74 cm mercury. Okay, 74 cm mercury, yeah? Because the length of the mercury column is 74 cm mercury.
A manometer is a device similar to a barometer that can be used to measure the pressure of a gas trapped in a container. A closed-end manometer is a U-shaped tube with one closed arm and one arm that connects to the gas to be measured and a non-volatile liquid, which is usually mercury, in between. As with a barometer, the distance between the liquid levels in the two arms of the tube, which is H, is proportional to the pressure of the gas in the container. An open-end manometer, figure B and C, is the same as a closed-end manometer, but one of its arms is open to the atmosphere. In this case, the distance between the liquid levels corresponds to the difference in pressure between the gas in the container and the atmosphere, which is P, or pressure atmosphere, is equal to pressure of the gas and pressure of the distant H.
Talaga no? Anong sana?
Ano rinig sa left tsaka right?
Ano, 0.5 dito, tapos sa left.
Positive 0.5.
Sige, kayo mo.
Negative 3.
Negative 3.
Ano?
0.5 sa...
Tanggalin nga ulit. Tanggalin mo ulit. Sige, tapos baba mo. Ayun, may ano doon. 2 point... Ay, yan yun.
May puti ba? Diba? Meron na.